Hello, young scientists. It's Friday again, and we're ready for some more science. We've been talking all week long about weathering and erosion and deposition, and we've looked at 4 lessons on that. So we need to move on and take a look at our next topic in this unit, and that is this question. How do movements of the crust change Earth? What? Is that like crust on your sandwich bread, or what is it talking about? Well, we're going to find out what the crust is in a minute. What do you think's going on here? Is this like an astronaut on the red planet of Mars, or what is it? I believe this is a scientist at a volcano. It's hard to tell, but I believe so. We're going to talk about volcanoes in our lesson today. Have you ever been to a volcano? I have been one time. Actually slept on the side of a volcano, believe it or not, when I was in Costa Rica. I'll tell you more about that later. But volcanoes are caused by the movement of the Earth's crust. And so are some other things, which we're going to learn about in this lesson. Now, I'll go ahead and tell you it's a little bit longer lesson today. So get comfortable because I want you to listen all the way through. And it has a lot of information in it. And so we've got a lot to learn in this one lesson. But don't stress out. We'll go back and review this stuff that we're going to learn today plenty over the next couple days, next week. So don't stress out. We've got a lot to learn. And they're going to use some big words today in the lesson, but you can do it. I need you to follow along in your book for sure today. So get your science book out and open it at page 381 so you can underline and take some notes if you need to and help you understand this kind of difficult topic we're talking about today. So let's get started. Moving on to page 382 in your book. If you look closely at a slice of bread, you'll see that the crust is very thin. Compared to the inside of the bread, the crust is thin. The same is true of the Earth. Earth's crust is its rocky outer layer. I feel like I skipped a page. Let me go back here. Oh, we did skip a page. Sorry. I knew there was a page between what I had just looked at. So I'm going to go back. This is 382. We went from 381 to 383. My computer didn't work. Let's look at 382 now. Inside the Earth. Have you ever dug a hole in the ground? What do you think you would find if you dig a hole all the way to the Earth's center? I don't recommend you do that. You probably couldn't anyway, but you'd burn up if you did. It's not really possible to dig a hole to the center of the Earth, but scientists have done research with technology to learn what is beneath Earth's surface. The Earth is a sphere, like a ball, made of many different layers. So when I always see this picture, I think of those big jawbreakers. Have you ever had a jawbreaker? Different flavors as you get to the next layer, it changes flavors. And then you finally get to the center, it's a different flavor. I always think of that when I see this picture because these are the 4 layers of the Earth. The outer layer that you and I walk on is called the crust. It's the thinnest. Under the crust is the mantle. Under the mantle is the outer core and then the inner core. So those are the 4 layers of the Earth. Let's read more about it now on the page that we started reading a minute ago. If you look closely at a slice of bread, you'll see that the crust is very thin compared to the inside of the bread. The same is true of Earth. Earth's crust is its rocky outer layer. So if you look right here, this layer right here looks like a slice of pizza or watermelon or something now. This rocky outer layer is the crust. It's very thin compared to the other layers. The crust is hard and made of many minerals. Earth's crust is thinnest under the oceans and thickest under mountains. The crust makes up only about 1% of the Earth's mass. So the crust is this thin. If you were eating a piece of pizza, that's where the crust would be. That's a good way to remember it, okay? The crust is on the outside layer of the Earth. The layer below that is the thickest layer. It's the mantle. The layer below Earth's crust is the mantle. The mantle is the thickest layer, making up about 2/3 of the Earth's mass. The mantle contains some liquid rock, but is mostly solid. High heat and pressure in the mantle cause it to flow like warm plastic. Warm plastic, kind of like gooey, isn't it? So there's a lot of heat here, and this rock can be molten like lava. And then at the center of Earth is a core made of metal. Now, there's 2 parts of the core. The inner core is solid iron and nickel. The inner core is the innermost part, the very center here. It's solid iron and nickel. The outer core, this part right here, is molten liquid metal. So that's the hottest part right here. It's the melted part. I think of lava when you think of the outer core. The metal core makes up about 1/3 of the Earth's mass and is extremely hot. So the center of the Earth is very warm. So there's the 4 layers of the Earth. Let's go back to this page now because it was asking us to match them. What's the largest portion of the Earth's interior? It's that orange part. It's the mantle. What's made of molten metal? That's the outer core. What's made of solid iron and nickel? That's the inner core. And what's the thin, rigid rock layer? That's the crust. We've got to know these 4 layers. All right. Plate tectonics is the next thing we're going to talk about. You can see objects in motion all around you. Did you know the surface of the Earth beneath your feet is in motion too? What? Well, let's read about it. Earth's crust is a hard shell of rock, but it's not one solid piece. Many pieces of it, called plates, fit together like a jigsaw puzzle. The plates rest on Earth's mantle. If Earth's mantle flows like warm plastic, do the plates move too? Yes, they do. The motion of the Earth's plates is very slow. However, it happens too slowly to see. The theory that Earth's crust is divided into plates that are always moving is called plate tectonics. All right, now when you think plates, don't really think about like dinner plates you eat off of, but think of big puzzle pieces, okay? So if you could take a globe and flatten it out and make a flat map, here are the different plates or the different puzzle pieces that tend to move around. So you can see, I'm not going to name them all, but here's where we live. The United States here, it's the North American plate. And you see it touches right here, the Juan de Fuca plate. And down here it touches, I can't see now, I covered it up, but all these different plates meet at different places. All these different puzzle pieces meet at different places. Some plates contain mostly continental crust. Others contain mostly oceanic crust. Now, what do you think that difference would be? Well, continental crust would be like the place where it's land, like North America, right? North American plate would be continental crust, but out here between North America and Philippines or Japan, China, is the Pacific Ocean. So this is the Pacific plate, so it contains oceanic crust. Many plates are made of a combination of the two. That would be where the plate is kind of partially on land and partially over water. In some places, plates are moving toward each other. In other places, the plates are spreading apart. So now, if you look in different places where you think about there's a lot of earthquakes or volcanoes, I was down here in Costa Rica, right about in here. And if you look, that's where the Caribbean plate meets the North American plates and the Cocos plate. So there's 3 plates right here around Central America. And guess what there is in Costa Rica, right around this area? A ton of volcanoes. And we're going to find out why there's a lot of volcanoes where I was down in Costa Rica. It's because these plates kind of separate from each other and allow lava to come up through the Earth's crust. We're going to learn about that as we read on. The Aleutian Islands chain near Alaska formed where northern edges of the Pacific plates is pushing against the North American plate. The Great Rift Valley formed where the Arabian plate is splitting the African plate into 2 new separate plates. So these landforms it's showing us are places where the plates are meeting and forming new landforms. Did we skip a page again? No, I guess not. It felt like we left something off there. Certain land features form where plates collide. Others features form where plates separate. Mountain ranges, island chains, and enormous valleys are some likely signs of a plate boundary. Excuse me. So let's talk about plate boundaries. Plate motion might be too slow to see, but what do you think happens where 2 plates meet over hundreds of thousands of years? The landforms we see today give us clues. Tectonic plates move toward each other and spread apart. Plates also slide past each other. Different types of plate motion produce boundaries that shape different landforms. Continental plates moving toward each other push up mountains. When an oceanic plate moves toward another oceanic plate, one of them is pushed down under the other, and this collision can cause a deep ocean trench and an arc of volcanic islands to form. When an oceanic plate collides with a continental plate, the denser oceanic plate sinks under the continental plate, causing mountains and volcanoes to form along the boundary between the plates. When plates pull apart, new crust forms on the ridge of both sides of the boundary. A lot of information, like I said today. It's a little bit hard to understand. But if we look right here, here's the Himalaya Mountains. Here's a picture of them. They're high, rocky mountains. And they're over here, and they're formed where these two plates are meeting, the Indian plate and the Eurasian plate. So the Eurasian plate and the Indian plate are pushing toward each other. So get your hands and do them like this. Here's the Indian plate. Here's the European plate. And just run your hands toward each other, and what happens? They push up, don't they? Okay, so that's how mountains form. When these plates push together over a long time, they can raise the crust and form these high mountains to where two plates meet and push against each other. Two plates can slide sideways past each other. Earthquakes occur often at these boundaries, as the San Andreas Fault in California. The North American plate is moving southward, and the Pacific plate is moving northward. So get your hands like this, put them side by side each other, and if you rub one way and the other, they rub together. Hear the friction? They kind of bump each other. That's what causes earthquake when two plates slide past each other. It makes the ground shake because they bump together. Two plates can pull away from each other on land. This forms a rift or separation. Iceland sits across the separating boundary between the North American plate and the Eurasian plate. It will eventually become two separate land masses. So here's the Eurasian plate, the North American plate. They're pulling away from each other, and you don't want to fall in that hole, do you? And so they're pulling away from each other, and it's causing a rift or a break in the land. And it says eventually they're going to pull far enough apart where it's that Iceland is going to be two separate pieces of land. As two continental plates, we just looked at this a minute ago, move together, their edges fold and bend, pushing up mountain ranges. The Himalaya range in Asia includes the world's highest mountain peaks. The Himalayas are still growing today as the Indian plate pushes against the Eurasian plate. All right. So you got three different things we see on this page that those big plates, those big puzzle pieces on the earth can do: rub together and form an earthquake, pull apart and cause a rift or a big trench, a big hole in the ground, or push together and form mountains. So let's talk about those three things. The first one is earthquakes. Movement of whole tectonic plates is very slow, but once in a while, small pieces of earth can shake enough to crumble buildings to the ground. A fault is a break in Earth's crust where rock on one side can move in relation to rock on another side. So it's like the two places where the two plates meet. As plates move, pressure builds up along the fault. When the pressure becomes too great, the rock on one side of the fault suddenly snaps free and slides past the rock on the other side. This release of energy and shaking of the ground is called an earthquake. So here's two different plates. Here is where they are rubbing together. So they're rubbing together, they're stuck together, then all of a sudden they break free and the ground shakes and it makes an earthquake here. The fault is the place where one side can move in relation to a rock on another side, or where two plates meet. The point inside the earth where the earthquake begins is called the focus. You saw it here. So right here where these two pieces rub together, that's the focus, the focal point of the earthquake. The energy from an earthquake travels away from the focus in waves. When the energy waves reach the surface, the ground shakes. The point on Earth's surface directly above the focus is called the epicenter. Earthquake motion is most severe at the epicenter. So you can see in your book, but you can't really see because I've got it digitally here. Right above this place, right above the fault line, is the epicenter. It's where the earthquake is going to be the strongest. It's where the ground is going to shake the hardest, at the epicenter. Smaller waves of energy occur near the focus before an earthquake. The tremors may not be felt at the surface, but a device called a seismograph can graph them. Scientists can use a seismograph to predict if an earthquake is likely to occur. There's no way to prevent earthquakes, though. You can't go grab hold of the tectonic plates and hold them still, can you? To avoid injuries during an earthquake, avoid buildings, bridges, or other structures that are likely to fall down. Earthquakes can be dramatic and can cause great damage to built structures. So I know when I was in school, we haven't done one here, but we should do earthquake drills. We haven't done it in a long time here at Russellville, but we would get under our desk in case a piece of the ceiling might fall when it shook. The desk would keep it from hitting us in the head, I guess. And here shows the energy waves, those red lines coming out. So words to know on this page: the fault line is where the two plates meet and can rub together to form an earthquake. An earthquake, obviously, is the ground shaking. And then you got your epicenter, the place on the surface right above where the earthquake occurs. And then you got the energy waves. The focal point, too, is down in the earth where the plates rub together. And so measuring earthquakes, how do you measure an earthquake? How do scientists describe the strength of an earthquake? Do they measure the size of its energy waves? Do they figure out the total amount of energy it produces? They do both. An earthquake's magnitude is the amount of energy it releases. The Richter scale measures the magnitude of an earthquake on a scale from 1 to 10. So if you ever hear on the news that there was an earthquake, they would say it was a magnitude 6 earthquake on the Richter scale. So the Richter scale is just a measuring point, just like a 1 foot is 12 inches, okay, that we can measure in inches. Well, you can measure how big or how rough, how much energy an earthquake had on a scale from 1 to 10. The bigger the number, the worse the earthquake was. The scale uses the size of waves on a seismograph to determine an earthquake's strength. An earthquake that measures 2.0 on the Richter scale is too mild to feel. About 8,000 earthquakes measuring below 2.0 on the Richter scale occur every day. So we might have one and we wouldn't even know it just because you don't really feel it. It's too small to feel. Each 1 point increase on the Richter scale means an increase of strength of about 31 times. An earthquake measuring 6.0 or higher on the Richter scale can cause heavy damage in populated areas. Earthquakes measuring 6.0 or stronger occur about 120 times per year. The Richter scale was developed in 1935. Scientists have since developed a more accurate way to measure the magnitudes of larger earthquakes. The Moment Magnitude Scale, or MMS, uses a mathematical formula to calculate the total energy that an earthquake releases. The Moment Magnitude Scale also assigns numbers between 1 and 10. In January 2010, an earthquake measuring 7.0 on the Moment Magnitude Scale caused catastrophic damage to a densely populated area in Haiti. So here's some measurements of bad earthquakes in Chile in 1960. A 9.5 out of 10. Can you imagine how bad and scary that would be? In Russia in 2006, an 8.3. In China in 2008, a 7.9. Haiti in 2010, 7.0. Chile again. Chile has a lot of earthquakes. It must sit right on the fault line where the two plates meet. An 8.8. In Japan, 2011, the most recent one on here was a 9.0. Not only did it cause an earthquake, but it happened down in the ocean, and it caused a tsunami. It caused a lot of flooding, too. The earthquake can shake the ocean water and cause it to form huge, huge waves. Which of these locations would experience greater damage in an earthquake, a city or the country? Well, if you shake the ground, these buildings could fall, couldn't they? So obviously a city would have more damage than the country. Volcanoes. The heat and pressure in Earth's interior are intense enough to melt rock. Does that liquid rock ever make it to the surface? Yes, it does. There's some of it right there. The liquid rock below Earth's crust is called magma. We might call it lava sometimes too, but the scientific word is magma. At boundaries where plates are either moving toward each other, pulling away from each other, or at hot spots in the middle of plates, openings in the crust can occur. A volcano is an opening that allows magma to reach the Earth's surface. Lava is the molten rock that erupts from the volcano, along with ash and hot gases. So inside the Earth, it's magma. When it comes out, it's lava. The shape of a volcano depends on how that volcano erupts. Some volcanoes erupt explosively, spewing lava, ash, and gases high into the air. Other volcanoes erupt with a slower, steadier flow of lava. Remember, I told you at the beginning of the lesson that I had slept on the side of a volcano here in Costa Rica, and it was in the city of La Fortuna, and actually it was at a water park on the side of a volcano called Baldi. The volcano is called Arenal. Volcan Arenal is what it's called in Spanish there. And the lava only flows down one side of the volcano. We slept on the other side. So one side of the volcano is all this, it's no plants at all. It's lava flow. The other side is a rainforest. And right in the middle of the rainforest is this water park with waterfalls that are actually heated by the lava inside the volcano. And so I was up on a volcano with a waterfall, like shower water. It was so warm. Letting that flow over my hair, and then the higher up on the volcano you got, the warmer the water was, and you could go down a little bit lower and be more cool. But that was one of the coolest things I've ever done, is be on the side of a volcano on a water park. And they had beautiful pools. It was a rainforest. There's parrots flying around and everything. Kind of a tropical paradise. One of my favorite vacations ever. My wife's mom is from Costa Rica, and we had gone to see her family, and they took us to this place, which was so nice. I want to go back. Non-explosive lava flows form shield volcanoes. Look at this shield volcano. It's kind of flat. Broad sheets of lava steadily build up to form the wide, low shape of a warrior's shield. The island of Hawaii is made up of 5 shield volcanoes. The one that I was on, that I slept on the side of, was a shield volcano as well. It was relatively flat, not real steep. Explosive eruptions from cinder cone volcanoes cinder cone volcanoes. Lava explodes into the air and quickly hardens. Fragments fall and collect to form the volcano's steep slope. Paracutin is a cinder cone volcano in Mexico. Alternating types of eruptions form composite volcanoes. Explosive eruptions produce the steeper slope, and liquid lava flows cement the fragments in place. Mount St. Helens in Washington State is a composite volcano. So 3 different types of volcanoes. A shield volcano, it's not explosive, just a small lava flow like the one I was on. The lava always flowed on one side. The other side was no lava flow. On the one I was at, these cinder cones, they're probably one of the most dangerous. They blow up. They're explosive. And the composite can be either one. It can have a big explosion, or it can have just a small lava flow. Can maps help us see patterns? Well, we've just talked about the place of volcanoes, that they're at places where the 2 plates of the earth kind of separate and let some of the lava come up through, the magma come up through. Are there particular places on earth where they're most likely to occur, where volcanoes are most likely to occur? Let's find out. So if you're looking at this map here, the red is a mountain, the little greenish is an earthquake, and the orange is a volcano. So aren't they all pretty close together? Don't they form a pattern? Look out here, through here. This is out from Hawaii. You got all kinds of volcanoes out in the ocean here. I bet that's where 2 plates touch, don't you? And here's where the Pacific plate meets the North American plate, all through here. And so you see there's volcanoes, lots of mountains, and lots of earthquakes through here where those 2 plates meet. Over here in Tennessee, we've got some mountains, don't we? Don't really have any volcanoes. Every now and then we have a small earthquake. I was down here in Costa Rica. We've got volcanoes, mountains, and earthquakes. Wow, look at this left side of South America. It's just covered with all three. Then over in Asia, it's kind of more spread out. But then you see definitely little patterns, little lines. Those are places where the different plates meet. You can kind of see them in the patterns. Okay. Use the map key to explore the locations of volcanoes and earthquakes, mountains and trenches on the ocean floor. Describe the pattern of ocean trenches. What can you say about the location of earthquakes, volcanoes, and mountains on the ocean floor? All right, so imagine the ocean floor now. Definitely lines, huh? Can you see those patterns? I mean, they just form almost lines. And so that is the place where the plates meet. So the different plates where they meet, that is where there's most likely to be a volcano and earthquakes and mountains and deep ocean trenches. Pretty cool. All right, so let's sum it all up. What is Earth's liquid metal layer? The liquid layer is the outer core, remember? The rigid rocky layer of Earth. Rocky layer, that would be the crust, wouldn't it? The thickest layer of Earth would be the mantle, and the solid metal layer would be, that's the inner core. And an opening in Earth's crust where magma can reach the surface is a volcano. Let's see if we can summarize it here. Pieces of Earth's crust move in a process called plate tectonics. Motion of the plates causes pressure to build up. Is that right? I have to look down here. We got our key down here. So motion of the plates, I got it right, cause pressure to build up. Eventually, the pressure causes rocks on one side of a fault, with the place where two plates meet, to snap free and glide and slide past the rock on the other side. This shakes the ground, producing an earthquake. The point inside the earth where the earthquake begins is called the focus, and the epicenter is the point on the earth surface directly above the focus. All right, here's some words. Now, these words are all scrambled. Let's see if we can figure out what they are. The strongest surface point of an earthquake. That would be the focus point, right? That would be this word, focus. This contains most of the Earth's mass. It's this biggest part. That's the mantle. A break in the crust where rock can slide past other rock. That's a fault. Shaking ground in a moving fault would be an earthquake. Earth's outermost layer, that's the crust. The point where an earthquake begins, that's its epicenter. And Earth's innermost section, made of two layers, that's the core. You're going to have an assignment today. You'll have these, and you've got to match the right words. So I just told you the answer, so that should be easy. True or false? The temperature of the Earth gets colder the closer you move towards the core. That's false. It's very, very hot in the middle of the Earth. The closer you move to the core, the hotter it is. Identify each type of volcano. Well, this one's the easiest. That's shield volcano. And then you've got a composite volcano. I have to go back and look. It's hard to tell the difference in those two. So we've got the one that's kind of more of a brownish color. Looks like it's got more rock on it. That's the composite. And the one that's kind of more brown is the cinder cone volcanoes. So let's see. I think then this one would be a cinder cone, and this one would be a composite. Describe the process that's causing the Himalayas to continue to grow. Well, that's where two plates, remember, are pushing against each other and causing the ground to go up to form mountains. Compare and contrast the Richter scale and the moment magnitude scale. Well, there are two different scales that measure the intensity of an earthquake. The Richter scale measures it on a scale of 1 to 10, and so does the moment magnitude scale. Explain the difference between the two seismograph readings. So if you were to look at a seismograph, imagine the bigger wave, the bigger it would be the greater the size of the earthquake, the magnitude of the earthquake. So this one, yeah, the ground shook a little bit, but look at this one. It shook, whoa, it shook a lot. So this would be seismograph reading that had a more magnitude, an earthquake with a larger magnitude. All right. So a seismologist is a person who measures earthquakes. We're going to read more about that later, but we're going to finish up this long 30-minute lesson from today because you're probably tired of listening. Now you will go and do a quiz on these 7 words for me now, and then you're finished with science for the week. We'll do some more next week. See you then.